So, hello everyone. I am Ziad Ali. I am a teaching assistant working in Gulf University for Science and Technology, and I am also a postgraduate student in the Computer Engineering department. Today, the topic of my talk is adversarial machine learning, which is a recently emerging field that deals with the security of machine learning systems. And so this is a typical scenario of cybersecurity where we have an attacker that tries to attack a machine learning model. For example, it could be a deep neural network or a random forest or other machine learning algorithms, and the defender has to try and defend the model from those attacks. So the attackers basically try to fool the model, meaning that they try to compromise the performance of the model and to make their predictions go haywire. So to begin, I'll start the introduction with the outline. I'm just going to talk about the introduction. So we'll go through what a deep neural network is, and then a convolutional neural network, and just threat model that we have in adversarial machine learning, and then applications of some of the attacks, some of the defenses that were proposed to counter those defenses, and then the conclusion and directions for future work. So a deep neural network is used to classify, for example, images or audio waves, or it has various applications. So in this case, we can consider, like if we have an image and we want an image of a cat or an image of a dog, and we would like to classify it as an image of a cat or a dog or a car, then we can consider the grid here to be an image. So maybe we can consider that it's an image of a cat. It will actually be divided into a certain number of pixels. Each row would have a certain number of pixels, and each column would have a certain number of pixels. So in total, we will have about R times C, rows times columns, number of pixels, and then we would feed it to the neural network. And then the neural network will basically, our goal will be to classify that object, and the input will basically propagate through the network. So each line here basically represents a weight, and each weight basically has a number associated with it. The input values basically get multiplied with the edges, and they get propagated through the network, eventually leading to us to the output layer. The output layer basically represents each neurons, and the neurons with the highest probability is usually selected as the correct classification. So our goal is to, for example, if we have an image of a cat, we would want the image of a cat to be associated with the neuron that represents the image, neuron that represents the cat label. So that's how deep neural networks work, and it has various applications. The previous structure for the deep neural networks was based on feed-forward, but it was later on improved by LeCun in the following research work when they introduced convolutional neural networks. So in those cases, they just take convolutions over the entire image, and those convolutions basically pass through the network, and that leads to a better performance. The key ingredient in convolutional neural network is that it identifies the pattern across the entire image, instead of comparing it to a deep neural network, which only specifies it at a certain in a certain range. So moving forward, I'd like to point out why are deep learning systems critical, because they're being vastly used in critical applications. So in oil and gas industry, it's being used to predict failures. And in medicine, for example, it's being used vastly in applications such as detection of cancer. So skin cancer, we feed images into the neural network, and we want to identify whether the image is benign or malignant. And in self-driving cars, for example, everybody might know about Tesla. They use those machine learning systems in order for the cars to basically identify the stop sign and the lanes, so they can drive themselves. So, and also in speech recognition, DNN finds various applications. And these are critical because if we were to make the predictions of a neural network wrong, if an attacker tries to attack the deep neural network and it causes, for example, the machine learning system to recognize a stop sign as a speed limit, then the car will basically overdrive instead of stopping, and that could cause major accidents. So we want to protect the machine learning systems against such attacks. So for this talk, I'll mainly focus on two of the major data sets that are used in machine learning. One of them is MNIST. It contains images. So for example, we can see there are rows and columns, and the MNIST contains 60,000 training images, and the labels that we have here are we want to classify digits from 0 to 9. And so we have 60,000 training images that we use to train the neural network first, and then we have 10,000 further images that we use to evaluate the performance of the neural network. In the case of Cypher10, instead of the numbers, we have actual objects such as airplane, bird, cat, deer, and so on. So we'd like to classify those objects. For example, image of a dog should be classified as an image of a dog. That's the goal of a neural network. And in this case, we have 50,000 training images and 10,000 testing images. In the first case, MNIST, it only has one channel, and the Cypher10 has 3 channels, RGB, red, blue, green. So it's a more complicated data set as compared to MNIST. So where can the attacks basically, where are the endpoints of the attack in the machine learning pipeline? The attacker could basically attack the machine learning classifier from a perspective of the training data set. So for example, they can manipulate the training data set and insert wrong images with incorrect labels, and that could compromise the performance of the machine learning classifier. On the other hand, an evasion attacker, what they do is they manipulate the test set. They make some changes to the test set, and once that test data set is fed into the classifier, it basically makes the performance go down. Another form of attack is exploratory, which means that the attacker basically tries to identify patterns from the predictions of a neural network, and they try to find some actual hints about what the training data set might contain. So these are the endpoints of the attack. So we will focus, for this talk, our focus will mainly be on evasion attacks, in which we manipulate the test data set and try to fool the model. So in this case, we have an image of a panda. And once we have trained the neural network in a standard way, the neural network basically classifies this image as a panda with 57.7% confidence. It's very confident that it's an image of a panda. However, we can calculate a very carefully calculated noise by using this algorithm, which calculates the noise by using the gradients of the model. And we can add this noise, a certain percentage of this noise to the original image. And then, even though the final image appears as an image of a panda to humans, it could appear to the neural network as a gibbon, which is basically a monkey with 99% confidence. So a neural network thinks that it's a monkey with 99% confidence, even though the image appears to us as of a panda. It's indistinguishable. So there are various kinds of attacks in under evasion attacks. There could be whitebox attacks, in which the attacker has complete access to the model parameters, such as the weights and the data set and learning algorithm. Gray box attacks assume partial access to the model. And black box attacks assume no information about the model. So attacker has access to nothing. And there are various attacks that have been proposed under each one of them. So what are the adversary's goals? What are the attacker's goals? The attacker's main goal is to compromise the performance of the system. So how can they do it? Maybe they can just try to compromise the confidence of the prediction. Maybe if it's an image of a cat, the goal will be to reduce the confidence from 99% to 12%. Another way would be to cause the misclassification. For example, we've seen an image of a panda. Maybe the attacker just wants to misclassify it as any other object. So for example, it wants to misclassify it as a car. Targeted misclassification occurs when the attacker wants to make a targeted attack a target label. So for example, if the attacker wants to classify an image of a cat as a dog, so in that case, it would cause a targeted misclassification. So those are the attacker's goals. These are just the metrics. So the classification error, in the standard way, we assume that it's just the number of test samples that the model misclassifies. The robust classification error, on the other hand, is just the number of perturbed test samples misclassified. What this means is that we have clean test samples, clean images, but the attacker could basically manipulate these images, and then once they are fed into the neural network, we check whether or not it identifies it correctly. And the total number of perturbed samples that will be misclassified is counted as the robust classification error. So a more formal definition could be that the attacker is only allowed to change the image by a certain amount. So in this case, it's identified by the epsilon. And so for example, in the set beta, we have some instances of x prime, and they are the distance between the adversarial example x prime and the clean image should not be more than epsilon. So this is used to measure the distance between a clean image and its adversarial counterpart. An adversarial counterpart, by that I mean when the attacker has manipulated the image. So here we have a black box attack. In this paper, the authors were able to print out the image of a washing machine, and its clean image is basically identified as a washing machine. However, once the adversarial noise is added and it's printed out again, the machine learning classifier identifies it as a safe, and if the amount of noise is increased, it makes it classified as a loudspeaker. Now we can see that it's visually indistinguishable to us. However, the neural network thinks that it's a completely different object. In this case, the researchers had no access to the model's parameters. They knew nothing about the model, and they were able to attack the model. In this case also, we have a segmentation task in which we have to identify the objects in the image. The segmentation neural network it correctly identifies that there are three dogs in an image with a certain confidence. However, when we apply adversarial noise to the image, the neural network totally misclassifies it as a trained cow and a person. These attacks could also occur in the domain of audio. So, and we can take an audio waveform that in the context of speech to text, so we want to classify the speech, an audio waveform to text. So in this case, we can take the original waveform and we can add some amount of noise to it, and then the classification basically completely changes. So it was previously classified as it was the best of times, it was the worst of times, and then after we apply adversarial perturbation, it is a completely different phrase. So these are some of the examples of the applications of the attacks. So coming over to the defenses, to counter these attacks, there were various methods that were proposed to protect against such defenses. One of them is called certified defenses that give a guarantee of robustness. So they give a guarantee that no attacker would be able to succeed more than a certain percentage. The others are less effective, and they could be classified as input pre-processing defenses and detection defenses. So in these two, the input pre-processing defense, what it does is that it applies a filter on the images and then it tries to feed it to the classifier. However, these defenses were basically broken one after another and found to be ineffective. The detection-based defenses only try to detect whether an image could be adversarial or not, meaning that could it have adversarial perturbation applied to it or not. The most successful defense that had stood the test of time is adversarial retraining. And in this case, what we do is we take the images, we apply perturbation onto them, and we retrain the classifier again so that it becomes robust to such kinds of images. So in this case, we have input transformations, and there are various input transformations that were proposed in the original work. However, in the latter work, they were broken by the researchers, and the accuracy of the model was reduced to 0%, which means it couldn't correctly classify any of the images. And another form of key-based, form of input transformation technique is the key-based technique, which tries to introduce a secret into the model. So they would try to manipulate the image, try to transform the image using a secret key. And so their idea is, as long as the key is hidden from the attacker, the adversary could not be able to find a noise that could cause a misclassification. However, in the part of our work, we have shown that this technique also doesn't work as well as the other defenses that have been proposed, such as adversarial retraining. Detection defenses, again, they try to take the input images and they apply, they take a particular model, and then they apply some changes into the model, and they use the predictions between the two models to check whether it exceeds a certain threshold. If it exceeds a certain threshold, they classify it as adversarial. If it doesn't exceed the threshold, they identify the image as legitimate. However, this doesn't guarantee that the image will be correctly classified. So in the latter work, the detection-based defenses were also found to be ineffective, as Nicholas Carlini bypassed 10 different detection methods to show that they are not effective. So coming over to the most effective defense, which is adversarial retraining. Again, in the normal case, what we do is we take the training images and we train the neural network. And after that, after we have done training the neural network, we evaluate it by using the testing images, and we check the performance of the neural network. However, in adversarial retraining, what we do is we take the training image batch, we perturb using PGD. PGD is a form of attack. It's an attack algorithm that we use to find adversarial noise. And once we have gotten the adversarial image batch, we train the neural network. So there's one hidden ingredient here, is that we need to perturb the images using an attack algorithm and then retrain the neural network. So initially, under a PGD attack, the robustness of the model is 0%. However, after training, this method found that on Cypher 10, the robustness based on attack images, on adversarial images, increased from 0% to 45% in the case of Cypher 10. And on the MNIST, it increased from 0% to 89%. However, they found that there was a natural accuracy drop of about 7%, which means that the images that were clean could not be identified as well and as compared to when we used natural retraining. So this adversarial retraining process was further improved by using surrogate losses. So they made some changes into the loss function of a neural network, and they found that it leads to some small improvements over adversarial retraining. So in the standard case, we have an accuracy of 47% against the PGD attack, while in the case of trades, for example, it jumped up to 50%, and in the case of MART, it jumped up to 55%. In both of the cases, only the loss function is changed in order to improve the robustness accuracy. So even though we have found that adversarial retraining is effective, we haven't reached the best performance yet. So the best performance that was achieved was about 50% using the trade's loss function. And on MNIST, it was about 90%. Why is there a vast gap between MNIST and CIFR10? It's because CIFR10 dataset is more complicated. It has more channels, and learning on CIFR10 dataset is harder. Learning robustly on CIFR10 dataset is harder than as compared to MNIST. So as you can see, CIFR10 achieves 45% robustness, and there is still a vast gap that we would like to address. And for the natural images, CIFR10 on a neural network trained on CIFR10 would achieve about 90% accuracy, 95% accuracy. However, under attacks, the accuracy is reduced to 45%. And this gap is basically what we would like to address in the future work. The technique in the previous work, they also proposed that this gap could be reduced if we use more training samples in the training process. So a higher number of samples that would be used in the training process could guarantee that we would achieve even a higher robustness against such attacks. So in the following work, the authors basically used extra data of about 500,000 more images than what we usually train the neural networks with. And the accuracy jumped from 45% to 59%. And in the following work after that, they used different kinds of data augmentations. So they would manipulate the images by adding some patches into the images so that they generalize better. And this method basically achieves a robustness of about 66.56. So there's still a gap between the robust accuracy, which is about 66%, and the standard accuracy, which is 90.51%. So there's still a gap, and this has a lot of room for improvement. So either we can use extra data to make models more robust, or the authors suggested that maybe we can make some changes to the architectures of the model in order to enhance their performance against the attacks. So here we have a typical resonant architecture. It's heavily being used in as a default architecture in object recognition tasks. And in this case, the input image, we pass it through the neural network, and it goes through certain convolution layers, and we receive 64 feature maps of size 32 by 32 after the first block, the first layer of the resonant. By making changes to the architecture of the model, we can try to protect against such attacks. And how can we make changes to the architecture so that it's better against the attacks? We can use more feature maps. There was a following work which suggested that we can use a higher number of feature maps in the architecture of the model, and that could lead to an improvement on robustness as well. So one way is to improve the robustness by adding more training images to the neural network learning algorithm, or it could use, or we could make changes to the architecture and improve the robustness based on that. And in this work, they found that indeed making the neural networks wider, meaning using more feature maps, could lead to an increase in the robustness. So coming to the final slides, we have, this is a website that basically tracks the best robustness that is achieved on CIFR10 so far, on the CIFR10 dataset. And we can see that the number one method has a best known robust accuracy of 66%. There is still a gap between the standard accuracy and the robust accuracy. So this model is still vulnerable to attacks by an amount of 24%. And this is on CIFR10 dataset. On ImageNet dataset, which is a further more complicated dataset, the gap is even wider. So we have a robust accuracy of only 38%, And there's a vast amount of improvement that could be made and in this research field. So for as conclusion, as I've already mentioned, there are two main points at which we can make changes so that the robustness of these models could be enhanced. One is making changes to the architecture, and the other is adding more training images to the data set. And this is a part of, that could be a part of the future work, and researchers are still trying to figure out how to get the most robust model and protect against these attacks. And that concludes my talk. Yeah.